Okay, so this video is going to cover voltage from the perspective of calculus-based physics. Um, so um, what I'm going to sort of do, hopefully you've already watched the videos that sort of take V equals KQ over R for granted. I'm going to show you where that comes from and also show you how to get voltage for other things besides point charges. So we're going to figure out where the heck that comes from a point charge and use that newfound knowledge to get voltage for things we don't know yet, which are the line charge, the infinite line charge, and the infinite plane. In the same way that we get this, we'll get this. I'm going to show you, there's a couple of different ways to get voltage. And also, what I'm going to start off with before I do anything else is going to be a little bit of a Physics 1 review from the calculus-based viewpoint, so that if we really make sure we remember that stuff very well, then we're going to find that jumping over to the new stuff is going to be a lot easier. So first of all, let me remind you, just kind of from the energy perspective, that every object has a store of kinetic energy. When that's kind of your energy of motion, that's your classic 1/2 mv squared, motion of energy. And when forces act on it, we can either work in the force picture or in the energy picture. What we think of is that those forces do work. So if the force is nice and well behaved throughout the object's displacement, we just use this form, force dotted with the displacement. However, in many cases, the force does not do the same thing throughout the motion. So in that particular case, if we have some sort of motion through space like this, we break the little pieces of motion here, ds. ds may be like this over here, and maybe like this over here. Those are your little steps that you're taking. And in general, of course, the force may be acting different strengths or different directions relative to what you're doing. And so what you're doing when you're figuring out the work there is you're trying to figure out what is the overall thing that the force has done along your path. This is a reminder, if the force makes less than 90 degree of an angle here, it's going to do positive work. So this little contribution to the work is positive because the force, the angle is less than 90 degrees. And what that means is that the force is more helping you. And over here, for instance, there's going to be a little contribution to the work that's negative. That's when the angle exceeds 90 degrees. That's because the force is more working against you. And then, of course, it's also possible if the force is working exactly at 90 degrees, then it does not do any work. It doesn't mean the force is zero, but it's in more of a guiding role. I call it a guiding force. So really, in the picture, what we're doing here is we're asking, not does the force exist, but does it help or hurt the motion? And of course, the sophisticated way of doing that is, of course, really what we're asking for, does the work done by a particular force, if it's positive and the force is more with the motion, what it really means is it's putting in kinetic energy into the object. And if the work is negative, more acting against the motion, then it's actually removing kinetic energy from the object. So I like to think of work as kind of like the deposits and withdrawals on a bank account that you have. That bank account is not in dollars, but it's in kinetic energy. So positive works are deposits and negative works are withdrawals. And of course, this ties all into the work energy theorem, which is to say, this is you balancing your checkbook and asking, out of all those different deposits and withdrawals that you may have, some are putting kinetic energy in, some are taking it out. Some, they may be changing the trajectory of the motion as guiding forces, but they're not adding or removing motion energy. But ultimately, you're asking, do you have a net increase, decrease, or constant balance in your kinetic energy bank account? So that's usually a Physics 1 kind of thing where you first kind of do your homework on the work energy theorem. You learn what work means, you learn it changes kinetic energy, and then you kind of expand your picture. And if there's a certain type of work called a conservative work, then what we say is that the work done by that particular force just trades with another bank account here called potential energy. And so if it changes the kinetic energy balance, it say increases the kinetic energy, it comes from potential energy. And so there'll be an equal but opposite change to this other box. Of course, this is where if you rearrange this equation right here, you get your classic kinetic energy plus potential energy equals kinetic energy final plus final. So essentially K plus U, which we call mechanical energy, is conserved if you only have these types of forces. And of course, you can use those particular types of calculations to good use, not only in physics 1, but in physics 2, where these particles are flying around. But what I want to do is I want to take this and set it equal to the work, which is this. So we get this statement right here. So essentially, what this statement is a recipe for if you know the force done by something, this has to be a conservative force, then you can find the potential energy. And so you use this to great effect in physics 1 to get, for instance, from the force of gravity. From the force of gravity, you found a corresponding potential energy. Another common one that you do, I assume you did it in physics 1, you go from the spring force to getting a corresponding spring potential energy. And what I want to do is I want to look a little bit back at those things because they're really informative to our new stuff. So bear with me. I know this seems like a little bit of a review, but I think that you'll find that if we get solid on a few things, especially a few things that were probably glossed over when you were in physics 1, then we're going to be ready for some of the stuff that does pop up pretty weirdly in physics 2. So let me go ahead and start with the easiest one, gravity. So gravity, let's set the plus y direction to be upward. And so the force of gravity, of course, pointing downward, has a y component of minus mg. And we'll throw it into this formula. Delta u equals minus, and we don't need the dot product here. This is one-dimensional, fy dy. We throw that in here, minus mg. And let's figure out what our bounds of our integration are. I guess just generically, I'll call it y initial to y final. So if I integrate from y initial to y final, I will get delta u, which is the difference between y final and the potential energy at the final y, potential energy at the initial y. Let's see what we get. Well, that minus and that minus, the minus sign in front and this minus sign go away. The mg comes out, it's constant, assuming we're only going up a few meters or so, then the gravitational acceleration will stay constant. We get integration from y initial to y final of dy. There's not a whole lot to this. And of course, that is going to give us y final minus y initial, and I'll just multiply through the mg. So this is starting to look like your familiar formula. So you may remember this is mgy. Sometimes instructors prefer h. In fact, I prefer h in most cases. Y is just nice here because we're sort of, it's a little bit less abstract than integrating over h. So what we do here, I want to point out something, though, that this is really only giving us the difference in potential energy between two locations. We still have to make some decisions, and again, these decisions were oftentimes just kind of glossed over in physics 1. But I do want to point out that if, let's say, we look at our zero height y initial, if we integrate from there, then this will go to 0. But what that's saying is that the potential energy at my final height is equal to, solving for it from here, it's going to be mg y final plus, and then I'm bringing this over to the other side, whatever I want to set my potential energy to at the initial height. So if I ignore the final and I just kind of call this y instead of y final, there's my equation that I know and love, but it's actually saying here there is a constant, okay? So what is this meaning of this constant? Well, what that constant is that whenever I have my, say, baseball or whatever at y equals 0, I can actually decide arbitrarily what potential energy I want to give it there. This is just some kind of constant. And what I'm going to just decide, I'm going to choose that at this height, I'm going to say my potential energy is 0. So I'm going to choose this constant to be 0. So that's what gives me my classic formula here, mgy. But I'm going to show you that even if there was a constant here, it wouldn't really have any practical difference in your calculation. The reason why is that delta U, okay, so U final minus U initial, if that would be mgy final plus some constant, and then mgy initial plus some constant, well, the constants work out to cancel, and there's no practicable difference in your response, okay? So delta U would still be the same regardless of the C value. So same delta U, same delta KE, regardless of what that C value is. It's kind of just like an arbitrary constant. It does not matter what its value is. Does not matter, okay? It will give you the same practical answer no matter what. It's kind of like just making a decision. And if you sort of need to think about why that is, okay, let's say we have a ball. It ends up starting here, or sorry, it ends up, let's say it starts from here. Well, I don't know, it doesn't matter if I throw it up or down. So let me say I throw it upward from y initial to y final. And from here to here, it has a potential energy change of plus 5 joules. Well, if it have energy going into storage, it means it's slowing down. The kinetic energy change is going to be minus 5 joules. What does it matter if this is potential energy here is 0 joules and here it's 5 joules? What difference does it make if I chose that constant to be, I don't know, 100? And so here it's 100 joules and here it's 105 joules. It's still the same change, right? If you need another example, if you go back here, if the integration of f gives you u, so if we look at the relationship between f and u, going this way, you integrate. To get back, of course, we take the derivative. Those are inverse operations. And so the reverse of that is that the fy is minus du dy, okay? And so essentially, if I want to recover the force, I take the negative times the derivative of the potential energy function. Now, if the potential energy function is mgy plus c, who cares what constant it has? If you take the derivative, the constant gets killed anyway, right? So gets killed regardless of its value. So no matter what this value of c is, it will produce the same force, right? And that's a real world measurable thing. So potential energy is a bit funny because you can add any constant to your formula that you want. It makes no practical difference to what the force will be, okay? Now, if you're wondering why I'm harping on this constant thing, it's because it does end up being important when we're doing some physics 2 stuff as to kind of mind what that constant is, because there ends up being some really strange choices that we make. But before I even move on from this example, I do want to point out a couple important things that that this statement really tells us, okay? Things that this statement ultimately is saying. I just want to kind of write it out in a list that's more clear. First of all, it tells us that force must always point most directly to lower potential energy values, okay? So that's one thing that it tells us. If you make a graph here of the potential energy function, right there it's mgy. Okay, so the potential energy increases with height, but of course we know that the force points towards lower potential energy. So the force is going to be negative y direction. This is just a statement about the two complementary pictures of force and energy. So if you have a ball, right, why does the ball fall down? We can explain it one of two ways, okay? One of which is that the force of gravity acts down. Another way to explain it is that, well, it's going from higher potential energy to lower potential energy. And so, of course, by that virtue, relating force and energy, the force is pointing towards lower potential energy. That's just a statement of what the two models say in terms of why a ball falls down, okay? Why does a ball fall down? It gets pulled down by the force of gravity. Why does the ball fall down in the energy picture? It falls, everything wants to get to lower potential energy. So the upshot of that is that force must always point direct to lower potential energy. And when I say most directly towards lower potential, of course, the ball will have the same potential energy at any height, at this same height, no matter where it is. And same thing here. And so you can see that the force is actually 90 degrees to the equal potential lines here. So the force must always point most directly to lower potential energy. And in fact, that means that sort of corollaries to that is that it's perpendicular to lines of equal potential energy, these lines I drew here. I think that so that I think I can't remember if I was going to say something else about it. Oh yes, and the other thing that it says is that if you have a potential energy versus y graph, force is literally the negative, I'll write out the word negative slope of the potential energy graph, right? So negative of u versus distance, or it's y in this case. So for instance here, the slope is positive, but the negative of the slope is the force. So it tells us the force points this way. And again, where is it pointing towards? It's pointing towards where the potential energy is lower, okay? So I want you to remember these statements here because they're the statements that are most important to us with how we're going to relate this to physics 2 material. Okay, so bear with me and be patient. I'm going to do one more quick example from physics 1, and this will make some kind of points in the same vein and reinforce it. Spring force. So spring force, if you remember, every spring has sort of an equilibrium length. And typically that's called x equals 0. The x-axis pointing this way. And then if you compress the spring from there, take it to a negative x value, the spring will push back towards equilibrium, so in the positive x direction. Whereas if you stretch it from equilibrium, well, the spring doesn't like that either. It has its happy place there at equilibrium, so it'll push back there. So if you take it to positive x values, it'll push in the negative x direction. And the law which relates all this is called Hooke's law, or the spring force law. This is the spring force law to tell us how much the force is. The force is not constant. If x equals 0, the force is 0. And if x is positive, the force is negative. That's what that extra minus sign is here is for, so that x and f can be different signs. Hopefully this is all perfectly reviewed here. And what we do next, same prescription. If we wanted to find the potential energy, now it's going to be integration. There's nothing going on except the x direction, so we throw it in there. We throw this force law in there, and what we get, let me integrate from x initial to, and then just let me leave the top kind of floating some x, instead of x final, I'll just call it x. That's going to be in our function. So I'll leave it to you to find that u of x minus u of x initial is going to be equal to 1/2 kx squared minus 1/2 kx initial squared. So we choose that the spring equilibrium is x equals 0. And so I'm going to say that's my initial. That's actually already baked into the Hooke's law itself. So if I choose that to be 0, this goes away. And what you see is my potential energy function is going to be like this. Here's the familiar part. What the heck is up with this constant? It could be anything you want. It doesn't matter, because essentially that's just like moving the origin of the potential energy. No matter what constant it is, it'll get killed when you take the derivative to get back the force. So we might as well choose it to be 0. Choose to be 0, and there gives us our classic function. If we want to plot this, it's a parabola u versus x. So we've chosen this to be 0 at the equilibrium. We choose there to be no potential energy. If you wanted to, you could knock yourself out. You could choose that to be, I don't know, you could choose that to be 1,000 joules if you want. That sets this to be 1,000 joules. 1,000. Okay, what does that get you? Well, it gets you nothing. That 1,000 joules is not like real energy. How are you ever going to get that out? Okay, if you want to pretend that there's 1,000, if you want to say there's 1,000 joules that's trapped in the spring and you can't do anything to get it out, go ahead, knock yourself out. You can put more energy in by stretching or compressing the spring, but you can't ever stretch it less than 0. And so there's 1,000 joules locked in there that you never have access to. You could go to a higher potential energy. You could go to 1,050, okay, if you wanted to, but by stretching it, but the most you can ever get out here is 50 joules. So what we might as well do instead is call this 0, call this 50, and essentially you get that same 50 joules out from the same motion. Choosing this constant to be 0 versus 1,000 is just, you know, a personal decision. It's like shifting the origin. So what do we get here? The slope is positive over here. In fact, it's positive kx, which means that the force, which is the negative of that, remember, the force is the negative slope of the u versus distance, okay? So the force is like this, it's negative, and where is it pointing to? Lower potential energy, okay? Remember, force always points towards lower potential energy, okay? And over here, the slope is negative, which means, in fact, it's negative kx. Remember, the slope of this, negative slope of this is the potential energy. The reverse operation of the integration is derivative. So this is the negative of the slope of this graph. So if the slope over here is negative, remember the force is the opposite of that. So where do these forces point? Force points towards lower potential energy, okay? So the force points towards the equilibrium because that's where the lowest potential energy is. That's the complementary of the force picture. So just like over here, where gravity was a little boring, it just went one way, okay? So here, if you have the spring equilibrium, there's higher potential energy to be had over here. When you compress the spring, there's higher potential energy had over here when you stretch it. But the lowest potential energy is at here, so that's why the force points that way. Force always points towards lower potential energy, okay? What we're really doing here These relationships are really setting us up for success later, and I guess I'm going to add this statement to it as well. Remember, integrating the force gets you potential energy, and taking the derivative gets you back the force. Remember, there's just a minus sign in the front, so there's a minus sign when you take the derivative, and there's also a minus sign when you take the integration. So there's that extra minus sign, but then there's just the integration and the derivative. Okay, so with that in mind, now we can move on to physics 2. Thanks for your patience. This statement, physics 2 finally, this statement right here, delta U equals minus F ds. Okay, I'm going to show you something that'll make our lives easier. First of all, we of course know that the potential energy of a charge, so potential energy of a charge and the voltage where it's located are related like this. And likewise, the force on a charge will be related to that charge times the electric field at that location. So remember, these are properties of a charge, an object. You can't have a potential energy of nothing. A charge has to be there to hold the potential energy. That's not quite true when you get to really more advanced physics, but for right now, potential energy, you have to have a charge that's holding it. And same thing, you can't have a force on nothing. You have to have a force that is acting on something, that's a charge. Whereas over here, these are properties of space, right? You can have, even if there's no charge in sight, at an empty location, you can still have a voltage. At an empty location, you can still have electric field. So what am I going to do with this? First of all, of course, the corollary to this is that if a charge goes from a location where the voltage changes, then its potential energy will change as well. So what I'm going to do is I'm going to plug this and this into my equation. And let's see, Q delta V equals minus QE dot ds, and the charge cancels just like that, and just like that we have come up with a relationship between voltage and electric field. Okay, so now we have a prescription for going back and forth between the voltage in a region of space and the electric field. Okay, if we want to go from electric field to voltage, we integrate, and as you can probably guess, if we want to go the other way, we go back and reverse it, we take the derivative. So what the derivative looks like, let me write this first. We can do this in the 1D radial direction, which of course the radial direction is what we've been working with a lot. So if you want to go from voltage to electric field, that's the integration direction, or sorry, from electric field to voltage. That looks like this, and then ER dr, and going back the other way, it's just the negative derivative. Okay, that's what we'll work with most. It is also possible to do this with 2D Cartesian. I'll just briefly mention it. I don't always get a chance to do this every semester, so I'm just going to mention it, and if I want to talk about it, I'll bounce it out to another video. You'll have to check the lecture videos to see if it's covered or not. So the way to go this way is delta V equals minus, and then the dot product here, remember component-wise dot product, that'll be EX dx plus EY dy, and then going this way, it's going to be each component. And these can be combined into a single statement, which if I do discuss, if I do cover that this semester, that obviously takes some explaining, especially if you've never taken vector calc yet. So again, I'm not going to say really any more on this. So more in other videos. Check your local listings. But right now I have a prescription on how I relate these two. And let me get into that. Now, one of the cool things about this Q canceling is that the things that I'm talking about, these are no longer properties of the object itself. These are just properties of space. So what I'm going to do is I'm going to go ahead and copy all the same stuff I said about how force relates to potential energy. I came up with the same equation. So let me go ahead and write down what I have here. So instead of force must always point most directly to lower potential energy, I'm going to write the electric field must always point most directly to lower voltage, which means that the electric field is perpendicular to lines of equal voltage. These lines of equal voltage, just to give it away, they're going to be called equipotentials now. These are very important in physics 2. We didn't really have a name in physics 1. And then the electric field will be the negative slope of the voltage versus distance, okay? So these are all important statements of how electric fields relate to voltage. And we're going to explore these statements thoroughly. The first thing I want to do is I want to point out how cool it is that these are now properties of space. So let's say our region of space, there's no charges around whatsoever, okay? Let's say I know that the region of voltage over here is higher and the region of voltage over here is lower. I know that the electric field is going to point like this, okay? The electric field points from higher voltage to lower voltage. In fact, if this is the higher voltage line and this is the lower voltage line, then the electric field pointing most directly from higher to lower, it's actually going to be perpendicular to these lines, okay? There's no charge in sight, okay? We're just relating these two spatial properties to each other, but we should probably double check now that, let's drop some charges in here and make sure that everything's cool. So we've learned about positive charges. We've learned positive charges like to go to lower voltage and they feel a force with the electric field. So whether you're in the force picture or the energy picture, everything makes sense, right? Plus charges feel a force from going with the field lines. They like to go to lower voltage, so it's definitely going to, if you drop it from rest, it's going to move to the right. That's because it had higher potential energy over here and it has lower potential energy over here, okay? So a positive charge falls to lower potential energy. Positive charge feels a force with the field line. Let's double check the minus charge. Minus charges like to do exactly the opposite, so are we going to have a problem here? Well, negative charges feel a force against the field line and they like to go to higher voltage. That's no problem because negative charges, when they're at higher voltage, they actually have a lower potential energy, have a higher potential energy over here. And so you can see that everything's all cool. Positive charges like to fall to lower voltage, negative charges like to fall to higher voltage. Everybody does it in the sense of going to lower potential energy. So both of these things agree with our original statement. Going back over here, force always points towards lower potential energy. So force points towards lower potential energy. However, it's really annoying to have it be that where the lower potential energy is dependent on what kind of particle you have, if it's plus or minus. So here, it's much more easy just to think about the space itself, okay? That the electric field points towards lower voltage. And that's true no matter what kind of charge we're dealing with, okay? So it gives us a way to like relate the spatial properties to each other without worrying about, do we have a plus charge in this space? Do we have a minus charge in this space? Maybe we don't have any charge in this space, but this still holds because this is a property of space, or I should say properties of space, right? Voltage and electric field. Whereas this thing, it depends on whether or not you have a plus or minus charge, and it just gets more confusing, okay? So here's what we have. Let me write down a few sort of corollaries here. So these are just going to end up being more important for physics 2. So let me start with this list, okay? So electric field must always point directly towards lower voltage. They're perpendicular to lines of equal voltage. And taking this statement, it also tells us that the electric field strength is tied to how rapidly V changes with R, with distance, okay? So you can see it right here, that the electric field strength is tied not to the value of V itself, but its rate. So not V value itself, okay? So just to give you an idea, let's say I have some region of space where the voltage is 1 volt, and over here where the voltage is 0.5 volts, the electric field will point towards lower voltage. There will be an electric field. If over here this is 1,000 volts, and over here this is also 1,000 volts, you might think, wow, big voltage. Well, the electric field is 0, okay? The electric field likes to point towards lower voltage. Here there's no lower voltage to point to. It sort of says, well, I don't have anywhere to point, so I'm just going to shut off, okay? The electric field is 0. But if the electric field is different over here versus over here, the electric field is going to point the way. It's going to point to how the way to lower voltage, and the greater the voltage difference is, if this goes down to, say, 0 volts, okay, that's a bigger voltage change with distance. In fact, then the electric field will be larger. Remember, the electric field is tied to the rate of change of the voltage, okay, not the voltage value itself, okay? Okay, so what I'm going to do here, I know that's a lot of abstract stuff, but the problem, of course, is that I don't have any charge distribution yet to kind of piggyback on. So what I'm going to do is I'm going to go ahead and tackle some of those and give you a chance to see this in more concrete terms. So first of all, let's do the point charge. Now, we already know the answer, KQ over R. That's the functional equation that you used in the earlier videos. But I want to give you a sense of where it comes from. So first of all, this is our prescription. We're integrating electric field to get the voltage. And of course, we know the radial electric field component, KQ over R squared. You throw that in there. And of course, the K and the Q are constant, but let me leave them in there for the moment. Minus KQ, integral of dr over R squared. I'm integrating from some R initial, where I'm going to reference the voltage value, and let's leave the top floating. And that will give me the voltage difference between where I finish and where I end up, or sorry, where I end up and where I start. And let's see, integration of dr over R squared, that's -1 over R. I'm going to kill that and that together. They're both minus. So what I get is this is equal to KQ over R minus KQ over R initial. Okay, so this is where all that business about thinking about constants is important. You might say, well, let's set the origin R initial equals 0. So let's see what happens, just like we did with the potential energy function, right? We just went ahead and set the origin to be 0. If you don't remember where that was, right about, let me find it here. I got my notes a little out of order. So we decided at y equals 0 to set that there. Of course, y equals 0 does not pose any problem for that function, but here we do not want to put a 0 in there. That's not a good place to pick an origin for this particular function. I'm instead going to choose r initials infinity, really far away, because that will make that to go to 0. So what I have is the voltage function is going to be kq over r, and then bringing this over to the other side, what I want to set my voltage to at that reference point. So this represents the voltage at infinity. Okay, so this is the voltage at infinity. Again, you can choose what you want that to be. In fact, one of the homework problems asks about your strange friend who picks that to be a constant, and you're going to show it doesn't matter. I'm going to choose that to be 0. The conventional choice is you choose that to be 0, and therefore you get this function, okay? And that's the function that you can use to your heart's delight doing point charge problems. Let me go ahead and take a little spin with it. So first of all, if you draw V versus R for, let's say it's a positive charge, positive Q, we know the voltage looks like this. The voltage, the electric field looks something like this. And we can also know that this is telling us that the voltage lessens with distance. Closer by you have higher voltage, further away you have lower voltage. And indeed, the electric field line is pointing the way from higher voltage to lower voltage. In fact, if we were going to draw equipotential lines, or equipotentials rather, then of course, if you fix R, the voltage will be constant. So this right here, that's an equipotential line. Over here, there's another equipotential line. And what we said, again, is that the electric field must always point most directly towards lower voltage. In fact, it must be perpendicular to equipotentials. It is, okay? What we said is that the electric field is a negative slope of the V versus distance, okay? So let's check that out. The slope here is negative. Well, that means that the electric field radial component is positive, pointing the way towards lower voltage. So it's saying go over to larger R because that is where lower voltage can be found. Also here, the slope is decreasing. And so the slope, while still negative, is smaller, and so the electric field has died down, okay? So this is less, okay? And what we also said was that the electric field strength is tied to how rapidly the voltage changes with distance, not the voltage value itself. So if you look here, these are very steep drops. This is where the hill is very steep. There is a large precipitous plunge in voltage. Therefore, the electric field strength is very high. Over here, it's starting to flatten out, and so the electric field strength is less. Remember, the electric field is tied to how rapidly the voltage changes. And so you can see here that the equipotentials, if we were to draw them, let's say if this were 9 volts, then the 8 volt would be somewhere very close by. The equipotentials are very closely spaced. The 7 volt might be a little further away. They are getting further spaced. Essentially what we're expecting to see is that because the electric field strength is decreasing, the equipotential spacing is actually getting further apart, okay? So again, remember that the electric field is tied to the rate of the voltage change. So if we agree to draw these equipotentials at a fixed delta V, I don't remember if I mentioned that before, but the usual agreement is we draw them for fixed spacings, like every 1 volt or something. And so if this part is fixed, you can see that if the electric field decreases in strength, we have to find the distances between the voltages is increased. Okay, so if the electric field decreases, the equipotential spacing is going to increase. So we see that here on the point charge. The electric field strength is higher near the charge, the equipotentials are spaced very close together because it changes very rapidly. So if we draw these every 1 volt, okay, you can see that they're very closely spaced over here, and they start to get more and more spaced out. You start to have that delta R is increasing as the electric field strength is decreasing. For a minus charge, this doesn't really change very much. We know that electric field lines point towards a negative charge, like so. And we know if we draw the voltage, well, the negative charge is going to flip the voltage sign. It's going to look like this. So the voltage gets lower as you go close. So if this were like, I don't know, -1 volt, -2 volts, -3 volts, you can see the electric field is still pointing the way towards lower voltage. So it's pointing the way towards lower voltage. Slope is positive, electric field is negative, points the way towards where lower voltage can be found. Electric field always points towards lower voltage. It points perpendicular to equipotentials. And where the electric field is strongest, the equipotentials are most closely spaced. Okay, you have the big changes in voltage nearby, more gradual changes in voltage further away. And so that's for a point charge. What we're now have to do is use these same techniques to get to other charge distributions. The first of which I'll do is the infinite plane. So the infinite plane of charge, which we learned about in the last homework, the electric field points radially away and it's uniform. The electric field is sigma over 2 epsilon naught radially from the plane. So let's go ahead and find what is the electric field, the voltage function of this. So it's constant, so the whole electric field comes out. We just integral of dr, and we're going to integrate from some reference, R initial, to some final R value, and that'll give us the difference in voltage, 2 epsilon naught, and then integral of dr is just R, so what we're going to get is R minus R initial. So again, we have to set some sort of origin. Certainly we would not want to use infinity here for that, because this particular function that makes that blow up. But now let's try 0. That's actually okay. That goes away. And then our voltage function, sigma over 2 epsilon naught R, plus whatever we want to set our voltage to there. Okay. Now we've chosen R equals 0 on the plane itself. What do we want to set the voltage there to? I guess let's go ahead and choose it to be 0. So what we get is this. Let's go ahead and sketch what this looks like. This V versus R, well, we've chosen that at R equals 0, the voltage is 0, but then this is just a linear function with a negative slope, so it goes like this. Unless R itself is negative, then negative and negative is positive, so it's going to look, actually, I'm sorry, this is not correct. This is going to be positive R as well. Radial direction is just away in any direction, so I don't need this right here. What do we have here? It's a linear function. In fact, the highest voltage here is 0, which is it's actually the maximum value. And then it just goes down from there. It decreases voltage. So let's just double check here. The slope is negative, which means that the electric field is positive, so the electric field points that way, it's pointing the way towards lower voltage, okay? So that's the way it always does, okay, right? So this is the highest voltage, and this is lower over here, and lower over here too. Now, it's unfortunate, of course, since we had to pick an origin, that v equals 0 is actually the lowest value you can have. After that, it has to go negative. Of course, if you want to get lower than that, it's got to be negative. And you know, the slope here is constant, which means that the electric field itself is constant, which we already knew. Of course, that's the hallmark of an infinite plane. And so if we, for instance, released a positive charge right here and it flew off like this, okay, it would never reach a lower voltage. V is always decreasing, which means its potential energy is always decreasing by U equals QV, which means its kinetic energy is always increasing. And what that ends up meaning is that no matter how fast it starts, it's going to end up with an infinite velocity, which again is hopefully not surprising, because this electric field never dies. It's always there, always pushing the charge to go faster. So that right there is what the graph looks like. And then also, if we were to draw the equipotentials are going to be evenly spaced. Now, why is that? Well, if you look at this equation, remember that the electric field is constant, which means that the rate at which the voltage changes is also constant, which means that the equipotentials are evenly spaced. Okay, so if we had a point charge like this, the electric field was decreasing. That meant that the equipotentials were also getting further spaced. But here, since the electric field is uniform, the equipotentials have the same spacing. And in fact, for that reason, we don't even really need to use the differential form. We can just say like this, okay? So if you measure the distance between two equipotential lines, and then you divide it by, so this delta V, whatever this is, and then you divide it by the distance over which it happens, that's one way to get the electric field. And you have a couple homework problems on this. You can go ahead and not even worry about which one's initial and which one's final. You can just use an absolute value here. If all you care about is the electric field strength, just divide the voltage change divided by the distance that it happens, okay? That's perfectly fine. I guess I should also mention, I accidentally jumped the gun on this, but it is possible also to talk about this with a more conventional x-axis, if this way is plus and this way is minus. If that were the case, then this graph would look just a tiny bit different. The voltage versus x, of course, you go to lower voltage going in the plus x direction, but you'd also go to lower voltage going in the minus x direction. So it's kind of like I like to think of it as kind of a pyramid, okay? So you kind of roll off this pyramid. So I can't draw a pyramid, but essentially a positive charge would want to go off the pyramid this way to lower voltage, but if you released it on the other side, of course, it'd be still repelled by this plate, and it would want to go this way. Okay, so that is the plane of charge, and then finally, let's take a look at let's see if I can find a piece of paper. Let's go ahead and take a look at perhaps the trickiest one. In some ways, it is kind of has elements of both, an infinite line charge. An infinite line charge has some tricks up its sleeve, and in some ways, all this business about setting constants is really because this infinite line charge is so weird. So again, let's find the voltage of an infinite line charge. We've already got the electric field. Whoops, there's no minus there, excuse me. Epsilon naught r hat. Oh, I don't need the r hat, I'm just doing the radial component. Okay, lambda over 2 pi epsilon naught r, let's throw it in here. Lambda is usually constant here, of course. This formula assumes it, dr over r. And we're going to integrate from some reference point to some final r. And this integral will give us the difference in voltage where we end up versus where we started. Yeah, I was already jumping the gun. This minus isn't here, but it's of course right there. So let's see what we get. dr over r is actually natural log. Natural log being a bit of a strange function. Let's go ahead and try out what happens. Where are we going to take our reference? How about we take our initial as 0? Well, that's not going to work. Natural log of 0 is infinity. That's not a good place. Let's try infinity. Our ln of infinity is also infinity. That's not going to work either. So we're going to have to pick of something that's somewhere, anywhere you want, but except 0 infinity. So anywhere you want, but it better be finite, not between those two. And then that's where we're going to choose our origin. We're going to choose our origin there. So I'm going to choose my origin there, and then I'm going to write out my function minus lambda 2 pi epsilon naught, and then let me go ahead and just write property of natural log is I can just write it like this to be compact. So subtraction becomes division. Let me draw this weirdo function. Here's what it looks like. V versus R. It is a natural log function that is upside down because of this negative, assuming that lambda is positive. So that I am going to assume that. So positive lambda. I'll draw a picture of it in here in just a second. So it's this infinite line charge. It looks like this. And this here, this point, our initial, is where I have decided to set v equal to 0. Okay, that is some arbitrary point out here, our initial. Okay. Now, I might as well, alongside this graph, draw the electric field here. So we know the electric field points away from a positive charge, and we know that the higher voltage is close by and the lower voltage is further away. That's why electric field points towards lower voltage. And if we look here, if we decided to set the voltage to be 0 at some random radius, then higher voltages than that are positive, and when you cross over to lower voltages are negative. Okay, so here, when you're closer by than your reference point, the higher voltages are positive, and then over here, once you cross that point, your lower voltages become negative. Okay, so in order for the lower voltage to continue, at some point you cross over from positive to negative. Of course, with the point charge, we could have forced this to always stay positive because we set at r equals infinity, v equals 0. However, that is not an option here because this is a natural log function. So we had to just choose some point here to be the origin. Okay, we couldn't set the origin at infinity. Okay, so for instance, for the point charge, we choose that r equals infinity, the voltage is 0, that was our origin. For the infinite plane, we chose that r equals 0 is going to be the origin. But for this, the infinite line charge, r equals just some random value is where we're setting the voltage to be 0. So what does this look like? It's always nice to throw in a test charge over here. For the point charge, of course, if you release an object near it, this voltage does asymptote. And so eventually you're limited in how much voltage decrease you can have. So you asymptote out, voltage goes to 0, and then the, or I should say the voltage change has a maximum value And so the delta U and delta K will also have a maximum value. And so in many problems, you'll find that the V final, in fact, in all problems, you'll find that the particle, when it gets very far away, has a very nicely well-controlled final speed. And that's no problem. We talked about in the infinite plane, of course, that's not the case. The electric field pushes forever. And so the final speed of a particle is not infinity. Remember that I said that this was kind of the hybrid. If you drop a point charge near a infinite line of charge, when it gets very far away, it will be traveling, this is speed, not voltage, it will be traveling infinitely far, or infinitely fast, okay? The reason why is there's no bottom. It can always get to lower voltage. So there's always lower voltage, always a V decrease, always a potential energy decrease, always a kinetic energy increase, no matter how far you go. It seems kind of strange, and especially it's kind of strange when you think about the electric field. So remember, the electric field is the negative slope, okay? So this graph, it has a big slope at first, big negative slope, which means the electric field points very strongly away. Okay, that's close by to the object. The electric field is very strong. Over here, out here, this slope has died down significantly, so the electric field is weaker. And in fact, the electric field goes to 0. Okay, it goes as 1 over r, but it goes to 0. So, strange bit of mathematics here. The slope of this, which is the electric field, related to the electric field, goes to 0, but the value never does. This is one of the weird things about the natural log function. I'll leave that to you to ask your lab instructor, or sorry, your math instructor, how in the world a function never asymptotes, the value never asymptotes, okay? It always gets lower, and yet the slope goes to 0. So I'll let you ask your math instructor about that one. But in this particular case, even though the electric field does die to 0, the voltage always gets less, which means that there is no maximum speed to the particle. It will go faster and faster and faster and faster because there's always lower voltage to find. That's the line charge, and the culmination of thinking about all that constant stuff is that here we run out of the conventional places to pick the origin, and we have to just set it anywhere. In the problems on the homework, you'll either get told where you set it, or you get to choose, but then of course you have to be aware where you chose it, because any answers that you come out either are going to be dependent on that, or of course, as we mentioned, picking the origin doesn't really have any effect on the changes. So regardless of where you pick your origin, so regardless of where v equals 0 is set, you'll still get the same delta v's, same delta u's, and same delta k's, which again we must, right? These constants on the voltage and these constants on the potential energy, they get killed anyway when you take the derivative to get the forces or the electric field. So they're sort of arbitrary scaling factors in the voltage that don't end up being real measurable things. Okay, so and this video is getting a little bit long, but there's one last little thing I want to throw in here that is related to voltage, and then we can be all squared away with the kind of calculus stuff on this particular homework. So I want to talk about direct integration of voltage. So what do I mean by direct integration? So let's take a typical example, a ring of charge, central axis. I've seen this guy before, and in fact, we went ahead and we found the electric field strength of that. The electric field strength, if I can find where I stuck it, we found that if x is equal to 0 in the middle of the ring, Ex was equal to kqx over x squared plus r squared to the 3/2. That's just the x component. I don't need to put the I hat there, but that's also the electric field as a whole. There is no y or z component. So what we've been doing, of course, this whole lecture is finding the voltage from integrating the electric field. Now, that's not what I mean by direct integration. So there's two methods to find voltage. So finding voltage is you integrate the electric field. In other words, you are finding the voltage from the electric field. The second method is what I call direct integration, not using the electric field. You can certainly put this in here and it'll work, but I'll show you that sometimes this would be difficult. It's not particularly difficult in this case. The value is very difficult, or you don't even know the electric field formula at all. Finding it would be really hard, but here's what we can do. The same ideas that we used in our continuous charge distributions unit, remember we integrated that, we can actually do the same exact thing. If we know the voltage of a single point charge, well, we can turn this into differential form and we can do a similar type integral. Now, if you're thinking, oh man, that was really difficult, well, this is actually much easier because remember, this is a vector. So you had to think in terms of vectors, and this is a scalar, it's just a number. And so it's far easier to do it. You don't have to mess around with symmetries and think about how the vectors cancel. So if you take, for instance, like a dq right here, and you want to know what's going on here, this is going to contribute some small amount of dv here, but it's not a vector, it's just a number, okay? It could be a positive number or a negative number, but every single dq here is just going to contribute a number here. We don't need to worry about how those little vectors are interacting, right? So let me show you how quick this is. This is r. Okay, that's the distance from the dq to the point we're interested in. This is x, this is r. I'll go ahead and integrate pretty much the same steps. R is constant for all these, so integral of dq. We get kq over r, and just like the last time, this is square root of x squared plus r squared. And then we're done, okay? So kq over square root of x squared plus big R squared is our voltage function. You can see it's a lot easier to do because unlike over here where we're worried about, well, this dq has a dE that way, and this one has a dE that way, and their y components cancel, but their x components reinforce. None of that stuff, because this isn't a vector, it's a number. So you can see that was a very quick way to get this. You can try it yourself. You can get the same thing by integrating the electric field function, but sometimes you can just kind of do what I call direct integration. Just start with the voltage and think of your object as every part of the object has a dq, and those dq's contribute a little bit of dv, and then those dv's are just numerical values that are being contributed. So there are a couple problems on the homework like that where you think, what is this charge distribution? I've never seen it. I don't know how to integrate the electric field. It seems like it'd be complicated. Before you give up, just remember, try that out, and you might find it's actually pretty quick to do it, okay? That's especially true when you don't have any kind of symmetry here and you think, oh God, I gotta keep track of the x and y components both. Well, think in terms of this direction, and you might find that you can get your answer relatively quickly.